All right, so today, super low key. I'm going to do a little bit of an overview, particularly for number 7, because we haven't talked about one of the concepts. I mentioned it briefly, called a tear stream. So I'm going to show you what that looks like on the board, and then I've got an Excel spreadsheet set up to show you how that would work in practice. If you wanted to do it in Python or MATLAB, we could talk about that a little bit. But this is for balancing complicated reactor separator cycles. So this would be for the methanol synthesis loop, that reactor process. The rest of the problems should be kind of like really detailed homework problems, right? The only problem there is that if you make a mistake on one, it's going to cause a problem on the next, it's going to cause a problem on the next. So the goal is going to be to set this up all in a computer so that when you do make a mistake, not if, but when you make a mistake, you will not do this perfectly the first time. It's easy to rectify, because if everything automatically updates, then you can fix a problem at any part in the whole process, and then it will be resolved. Right? You may have to click a few buttons, but it won't be too bad. Okay, so the one we're going to talk about is for, I believe, number 7, and this is the use of a tear stream. So T-E-A-R stream. So we have the feed to a process. We will have a recycle come back eventually, but I'm not going to draw the full loop because that's the whole point of this. So we have a mixer, a reactor, a separator, a bottom stream, a splitter, purge, and then a recycle. So the idea behind a tear stream, so I'm not quite sure, I never remember, is this called the tear stream or is that called the tear stream? Regardless, is when you solve this, they should be the same flow rates. So I'm going to draw a dashed line here. The general idea is that we set up the reactor separator, instead of solving this sort of in one big go with like a complex system of equations. They could be a linear or nonlinear system of equations. What we want to do is we want to guess what we think the composition or the flow rate of this recycle stream is going to be, right? So in the case of problem 7, it is specifying what the recycle ratio is. So you will want to have the flow rate of this stream fixed, and then you will modify what you think its composition is. So to start the process, you're just going to guess. Just going to make it a reasonable guess, okay? Then, if we're guessing what this is, because we don't know if this is the right answer yet. This is the initial guess for a solving type algorithm. We know what our feed composition is going into the methanol synthesis reactor loop, because that's the product that's coming out of those condenser arrays, right? So we're removing a lot of the water that was formed during the syngas process. There's 3 condensers. It goes to a final temperature and pressure. You can use humidity to figure out what's the saturation pressure of the water at that condition, and you can figure out how much of that water has to be removed in those condensers. Is this shocking information to anyone? Okay, good. So we have a fully defined feed coming in from the condenser bank after the the syngas reactions. We're going to guess what the composition is coming back from the mixer, right? But we don't know its composition. This stream right here going to the reactor, well, that's really easy, right? Just add all the hydrogen here to all the hydrogen here. Add all the methane here to all the methane here. Add all the water here to all the water here. That's a simple just add 2 numbers together. So then we know what the flow rates and compositions of this stream are. If we know what the conversion of our products are or reactants are, Then we can do a material balance on a reacting system to figure out what the outlet is here. I generally would recommend using the extent of reaction approach. So you would just need to set this problem up as a function of the extent of reaction, and now we have the outlet of the reactor fully defined. Then we have the separator, and in this particular case, the separator is fairly sort of perfect. Right, we're removing everything pretty nicely. So following the design specifications of the separator for problem 7, we have our bottom stream, top stream. We're sending a certain amount to purge, so then we can directly calculate what this stream is. Right? So by guessing what the inlet is, every single one of these material balances is pretty straightforward to solve for. Now this product here at the recycle is not going to be equal to your initial guess. So what do? Well, we just copy the first iteration and paste it into the tear stream. And then your Excel spreadsheet will update, or your Python code will update almost instantaneously. Right? These are pretty easy calculations for a computer to perform. So then, boom, it does the calculation again. So then you copy, paste, boom, does the calculations again, copy, paste, does the calculations again, copy, paste. And eventually, this and this will converge to the steady state solution. So do you guys remember in your differential equations class, right? You can solve for the time resolved changes in an ordinary differential equation, but if you set dx dt or dy dt equal to 0, that's the steady state solution. So this strategy here is a way that we iteratively solve a transient differential equation to get to the steady state converged solution. So that's what we're doing in practice, and this is a nice little strategy to do so. Questions on this procedure? I also have an Excel spreadsheet set up about how we can do this. Any questions before I jump into that spreadsheet? Okay. Yeah.
So we have like conversion of CO2 would be in minus out over in.
Correct.
And then we can replace the out with CO2 in minus extent of reaction of like WGS.
So you'll have to set up potentially a system of equations to solve for what the extensive reaction are. So I'll cover that maybe after we do the tear stream example, but basically the conversion is in minus out over in, or moles reacted over moles fed. So from there, if you know the inlets, you can use that to solve for the outlet flow rates of the material that has the conversion listed. Then you can substitute in the definition of the extent of reaction. So that would be out is equal to in plus the stoichiometric coefficient times the extent of reaction. So for the reaction that you're looking to investigate, then you can solve for what the extent of that reaction is. Now, since multiple species participate in multiple reactions, your extent of reaction expressions may have two terms. So you may have to do some algebraic substitution to get an explicit expression for what extent of reaction 1 is and what extent of reaction 2 is. But once you've done that algebra, you only need to do it once. Because regardless of what the conversion is, regardless of what the feed composition is, you have an algebraic expression for those conditions. And then you can set up your spreadsheet to spit out the outlet compositions of the reactor. Does that make sense? Okay, so this is not problem 7 that I'm going to display. It's a oversimplified example. Problem 7 is a bit more complicated. Go make it big. Okay. So what I have here is just a simple reaction of A goes to B, and then I've just added in I as an inert just to show you what else you can do with this. So I've set it up, and this is my color coding that I use in my personal spreadsheets. Conversion is an input, so it's green. So that means, Michael, go ahead, you can change that number, play around with it. Okay? Purge, this is the fraction of the top of the separator that's purged, so we can play around with that number. The extent of reaction is going to be based on the conversion, so that's orange. Michael, don't touch that, right? That's calculated for you. The overall conversion, right? So this is single pass conversion. This is overall conversion, so you can see that they're different. Recycle ratio, that tells me how this process is solved. Now, in your case, your recycle ratio is fixed, so your procedure here would be a little bit different than this one. And then I have two tables here. One table is for the molar flow rates and one table is for the composition. Now, in the example that I've set up here, I'm solving everything in terms of the flow rates. You're going to have to actually be using the composition data table. So what I do here is I have A, B, so reactants, products, inerts, and then I just add up each of those three numbers for every single stream. So this bottom table is just 95 divided by 100, 0 divided by 100, 5 divided by 100, right? So it allows me to quickly double check, hey, did I make any mistakes? Nope, my mole fractions always add up to 1. So at least we're not making any horrible algebra errors in our calculation, right? So I've got a lot of consistency double checks built in here. So this is converged at the moment. So I have my tare stream that's being mixed with my feed. And then this is my recycle that has been copied over. And so this is a converged solution because these numbers are the same. 96.5, 11.7, 96.5, 11.7. So we can see a couple of things that we know about a reactor separator process. One is that you can have an accumulation of the inerts. So I'm feeding 5% inert gas, and in the loop it goes up to 11%. Or almost 12%. My conversion for single pass is 20%, but my overall conversion has gone up to 40%. That's because we're sending more A through the process again and again. So in this here, what I've done is I have just some design specifications. So the inert goes to the top. I'm removing 100% of B in the bottoms. Then I guess I'm just saying that there's a 10% A in the bottoms stream. So actually, I don't think I kept that up. That's 0. Yeah. So these are just whatever criteria I built this spreadsheet with. I don't remember all the details, but that's not important because yours is going to be totally different anyway. So let's say I reduce the purge to, let's say, 5%. Okay. Now look at my recycle. It's 131 of A, but 96 in the tare stream. So I've got this little button here that copies this. So what I can do is I can go copy, and then I can go paste special, just the values. So now I've copied over the last iterations to the tare stream, and look, it's still not converged. So then I can go copy, and then I can go paste special, values. And it updates again, but it's still not quite converged. So I have this button, which is a macro. Has anyone ever used a macro in Excel? So we're going to learn something new today. That does that process for me. So I just click the button, click the button, click the button, da, 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 da. It's copying and pasting, copying and pasting. And it looks like the inert is dominating the system, so 5% purge is completely insufficient. So let's make it 10% purge. See if we can solve to a solution that's stable. And it looks like we're getting to a stable solution slowly. And that's pretty close to converged. Not exactly, but it's close. Right? So now my overall conversion is higher because I have a lower purge fraction, so my recycle ratio is higher. And this allows me to kind of play around with my process specifications. Yes?
Can you teach us how to make the macro?
Yes, I'm going to do that right now. So this is also the same thing here. Let me delete that. So now if you're doing this in Python, repeating the same process over and over again is a loop, right? So you could do a while loop, so keep iterating until you get some tolerance, or you can iterate for 50 times, right? This code is so easy for Python to run on a modern computer that you can just have it run 1,000 times and it'll probably be done faster than the blink of an eye, right? So You can either just loop it a million times, or you can do the strategy that I'm showing you here in Excel. So you may have to add in the developer tab, right? So at the top here, it's developer, which makes you seem very fancy. So the first thing we want to do is we want to click record macro. Yes?
How do you get the developer tab?
You may have to go to, I don't know how you get the developer tab. I think it's under, maybe preferences,
Oh,
ribbons and toolbar.
it's customized.
I mean, a quick Google search will probably be faster than,
If you go file and then go to, I just did it 2 seconds ago, now I can't find the button. I think it's options and then on the left.
and it'll be different for, I think, slightly different forms for Mac. Yeah, question.
No matter like what your guess is, though, once it does converge, it shouldn't be breaking like any laws of physics or laws of mass conservation, right?
If you give it a reasonable initial guess, I think it should converge for these problems. So, but that may be dependent. But if you put like a negative number in, then maybe it's going to break it. So I would say put reasonable numbers in. So you can maybe just keep the same composition as the feed, as the recycle. So in problem 7, you're going to have to, problem 7 is a little bit different than this problem. So don't take this as gospel. This is just the strategy. You're going to have to use the composition of the recycle stream, but you know its total flow rate already. So you'll actually be working backwards. So you'll be using this information to calculate this information. So your cells will be green here and orange up there. I mean, if you follow my coloring convention. So assuming you can do a Google search and get the developer tab, so we click record macro. And then I'll just call this class example. Okay? So as soon as I click OK, it says stop recording here, so we're recording. So now what Excel is doing is every single thing that you do, it's going to turn it into code. Right? So make sure you only do the bare minimum actions that you need to actually accomplish the task that you want to accomplish. So what I'm going to do here is I'm going to select my recycle, Control C for copy. I'm going to go to the location where I want to do here, paste special, values only, OK, and I have done the action that I want. So if you want to do something more complicated and automate it, you can do a more complicated macro. Then I click stop recording. So now every time I run that macro, and so I can run it, so I can go to macros here, and I can go to class example, and I can click run, and I've done my macro. So what I can do instead is I can get a button, drag that button around, and I will assign macro name to class example, OK, and now I have a button, and when I click the button, it does the macro. Does that make sense? So we'll have this recorded so you can go back and refer to it. But this is the tear stream, and it's a very useful way. Particularly, this is the way that people solve complicated processes when there is no purge and no outlet. So if I were to run a Rankine cycle or a refrigeration cycle, that's a fairly unstable system of equations because everything depends on everything, depends on everything, depends on everything. So it's not trivial to necessarily just, boom, solve that with a complicated nonlinear solver. So what you sometimes need to do is to break that loop up. So if you're trying to make a refrigeration cycle and you're trying to decide what's my compression ratio, what's the pressure of the system, what's the temperature of the hot and cold side, right? You want to maximize your coefficient of performance when you're designing this refrigeration cycle. Or if you're defining a Rankine cycle, you want to maximize your power output, right? Based on the material properties of your steam and your steel for the boilers and things like that. And so you'll break the process up and you'll get those two close together and then you'll connect them and then the solver will be able to handle it because you need a good enough initial guess to get all these things to converge. Okay. So that's all I had prepared. So what we can do is we'll do some general Q&A, and then as soon as we're kind of satisfied with the general Q&A, I'll just stop the video and I'll just roam around and help people out individually with their projects. So question here.
What kind of tolerance are you looking for on the project? Like how close is close enough?
not too close. I mean, you're not going to get exactly the same number I am, right? Because you're going to be using nonlinear solvers, so your numbers are going to be off a little bit. I'm not super strict about getting it to 10 digits of precision the same as me, right? If you're within a couple of percent, that's perfectly fine. I'm much rather concerned about organized work and detailed notes and calculations, right? So if the numbers are a little bit off, but the work looks beautiful like this, you're going to be totally fine. Don't worry about it. And so for part 2 of the project, where you're going to slap on the energy balances on top of this, right? That one, I'm going to give you my flow rates. So everyone will be starting off with exactly the same numbers. There's a question here. No? Or Connor?
Would you consider posting like a sheet that just has the answers to like one significant figure of magnitude? So like you do on the homework?
Just email me.
Okay.
Email me and I'll respond. Yeah, you got it or not. Yeah.
Okay.
Yes. That's totally fine. Okay. So if I'm inundated with emails, I may give an order of magnitude estimate for the problems, but I usually just do it by email. And if you ask me, I usually will be like, yeah, you got it, or so. But if everyone asks me, then it might just be more efficient for me just to post the range. But so far, I have not ever had that problem where I'm so slammed with emails. That would be like a blessing, right?
Yeah.
That's what I like to describe as a good problem, that everyone in the class is so engaged with the project that they all want to succeed and they all ask me for every single one. That would be nice to have. Any more questions? Okay. Yes?
On the spreadsheet for the results,
Mhm.
you have a point that says like moles in, moles out, moles generated, moles consumed.
Mhm.
Is that referring to like the overall amount of moles? So moles generated will be equal to moles consumed? Or is that like to pick up any mishaps in our mole mount or atom mount?
Goal is there should be no mishaps. So the question is about the last problem. I think it's 9, right? So that is an overall mole balance. You can also do an overall mass balance in addition to that. So the overall mole balance, right, is you're going to have an overall extent of reaction for all of the reactions. And so you need to keep track of where are all my moles going. So you're going to have water leaving in the condensers. You're going to have your product ethanol. You're going to have your purge stream, right? So I want you to keep track of absolutely everything. So looking at the whole process, right, we got steam in, we got methane in. Don't have to worry about the combustion right now, right? This is just for the main products because you don't know how much methane you're burning, right? So you've got your methane to form the syngas. You've got your steam coming in, you've got your purge stream going out, you've got your product streams going out, and you've got your water that's being removed. So you got to keep track of all of those different moles, and at the steam reforming reactor and the methanol synthesis reactor loop, you're not necessarily going to be consuming and generating exactly the same number of moles. You're going to consume a certain amount in those reactors, and you're going to generate a certain amount. So that is an overall mole balance. The other thing you can do is you can take all of your A, B, C, D, E species. If you have another table with all their molecular weights, you can calculate the mass flow rates of all of them. And you can double check your total mass balance in addition to your total mole balance, and then you'll be super confident that you've not lost anything, right? But that is the good final capstone double check. Yes, I have not made a big mistake. That doesn't mean everything's perfect. It just means that you haven't lost mass, which is trickier than it seems, right? Okay, so I'm going to stop the video unless there's any more general questions, and then it's just a free-for-all. And then shoot me up if you have a general question, then I'll go to the board if there's a lot of people having the same question. Okay.